Okay, we've got a good crowd here, so I think it's time to get started. Hi there, my name is Jack Ploshnik. I'm a data scientist here at Splice Machine, and I want to welcome you all to our hands-on feature store and model deployment workshop, where I'm going to tell you a little bit about Splice Machine, the offering that it has, and then give you guys an opportunity to use it hands-on. So first and foremost, what is Splice Machine? Splice Machine is what we call the real-time machine learning company. We are focused singularly on real-time machine learning. Our whole goal is making predictions in milliseconds in real time on big data. And so that is our place in the marketplace. And so what exactly do we mean when we say real-time machine learning? You might be thinking to yourself, we don't really, do we do real-time machine learning in my organization? We certainly have machine learning models. What do we mean by real-time machine learning? There are a number of use cases for real-time machine learning. It could be a product recommendation algorithm on a website where a machine learning model is generated whenever a user goes to a new web page, recommending them to go to a particular product. And that recommendation needs to happen in milliseconds, in between when web pages are generated. It could be a failure prevention model in an industrial setting. One of the Splice Machine use cases involves foaming, where an industrial plant has chemicals, and foaming needs to be detected within those chemicals, or else the plant can trip and millions of dollars can be lost. A very common use case for real-time machine learning is fraud detection. If you have a financial or an insurance application, you need to be able to detect problems as they're happening so that you can adjust accordingly. Another common example that we see here at Splice Machine is enhancing the customer experience. Imagine if your organization has call center agents and you're able to give them a real-time machine learning prediction about what the person calling them needs to have fixed. You could decrease the amount of time your customers spend on the call center dramatically, saving your organization millions of dollars. So these are just a few examples of what we mean by real-time machine learning. They're predictions that need to happen quickly in the moment. So let's talk a little bit about real-time machine learning. What are the parts of infrastructure that are necessary in order to do real-time machine learning? And why has it been considered so hard? Why are so many organizations sort of not yet ready to do machine learning in real time at scale? Why are they mainly doing machine learning models, in batch? So we see these components as the key things that are necessary to do real-time machine learning. These first, at the top level here, we have sort of the machine learning workbench, the machine learning environment. You have to have a modeling environment. This is something that I think everybody is familiar with. This is your scikit-learn models. This is your H2O models. This problem of building models data scientists are very familiar with. Then, of course, you have your experimentation platform. Most times you don't build a model just once, you iterate on that model, retraining it, and you need a method to track all of that work. Something common we see in this space might be the open source project MLflow, for example. Then there's model deployment. This is traditionally done in a REST endpoint, increasingly done inside of the database, which we'll talk about a little later. One thing you'll notice at all companies that do real-time machine learning successfully is they have this idea called a feature store. A feature store is something I'll get into in more detail later, but just know that if you look at the companies that are doing real-time machine learning, all of them have something that looks something like a feature store. And then finally, you need the platform that the data itself is stored on. You need some kind of operational data platform, a key value store, a quick transactional ACID compliant database, and then you also need your analytic database or your data warehouse, your data lake, something along those lines. So what does the ML landscape look like today? Most companies only have a few of the pieces of the puzzle that are necessary to really do real-time machine learning successfully. Almost everybody is familiar with modeling and experimentation at this point. And some companies have even dabbled in deploying machine learning models as REST endpoints, but they might not have the level of transparency or the level of governance that they were hoping for when deploying these models, but certainly they're moving in this direction. Moreover, almost all companies and platforms offer an analytic data platform. They have their data warehouse, they have their data lake, they have Delta Lake or Hudi or something along those lines. They have the ability to do some analytic data. But the operational data platform, the transactional database, the extent to which it exists in the company, it's not tightly integrated with the machine learning environment. And machine learning isn't really able to take advantage of those quick real-time data. And so what is Splice Machine? Where does Splice Machine fit in this architecture? Splice Machine is a complete modular solution for real-time machine learning. We offer all of the components necessary to do real-time machine learning with a little twist. Instead of having a separate database for operational data as well as analytical data, we have a single hybrid database that does both of these things. And we'll get in more detail about that later. While Splice Machine is a complete solution, we believe that you can go end-to-end, deploy a real-time machine learning model inside of the platform. We're also modular. If you are happy with the modeling and experimentation platform that you currently use, maybe you want to keep your data warehouse, that's great. Splice Machine can fit into the existing architecture and fill the gaps where necessary. So this is sort of the big picture. This is what Splice Machine is. This is what is necessary to do real-time machine learning. I would think that many of the people listening are least familiar with the feature store. This is the piece of the equation that is new, the piece of the equation that is really only necessary for real-time machine learning. And so I'm going to spend just a little time on what exactly a feature store is and why it's so useful for real-time machine learning. So what is a feature store? A feature store is a central repository of features that are used for machine learning. All of the data from whatever sources they may come from, you have your real-time sources, you have your batch sources, they're streamed into a central repository and are then used for all of your machine learning applications. What exactly are those machine learning applications? The first thing that a feature store empowers is feature discovery. Because all of your machine learning features are stored in a central place, it's very easy to search those features and figure out which ones are available to them. Data scientists often spend hours, if not days, recreating features that other team members have already built. And that's simply because they didn't know that those features existed. When large organizations have different teams, those teams don't always communicate with each other perfectly. And a feature store gives you a way to share that information. Moreover, data scientists, because they have access to all of the features that their teammates have built, they can ensure that they're always using the most performant features. And a feature that has important signal isn't being left out. Second, feature stores can automatically build training sets for data scientists. One of the things we'll discuss in the hands-on workshop is that when you have real-time machine learning problems, building that training set can be particularly challenging. And the feature store abstracts much of that difficulty away from the data scientist. Third, feature stores serve features to deployed models in milliseconds. If you have a deployed model, say as a REST endpoint, being able to serve raw data to that model is one thing. But being able to serve transformed features, the features that have gone through your feature engineering pipeline, is an entirely separate challenge. And that's what the feature store makes possible. And finally, a feature store empowers end-to-end data lineage. When data is moving in real time and it's moving quickly, it can be easy to lose track of how features were generated, what data was used when. And the feature store gives you a mechanism to keep track of all of the data used in your machine learning process. This is particularly useful for model retraining purposes, particularly useful for tracking things like feature drift and model drift, and useful for governance purposes and regulatory purposes. So you can tell a regulator exactly why your model made a particular prediction at some point in the past. So now let's talk about how feature stores are typically built. The traditional way that feature stores are built is to use two separate databases. One so-called online database, which will be a key value store, transactional database, and one so-called offline database, typically a data warehouse. And these two data sources are linked with some kind of pipeline. This is an excellent architecture. It's sometimes called a Lambda architecture when things work properly, right? Data is added to one, it's then automatically added to the other, everything's great. Unfortunately, though, as I'm sure you're all aware, in the real world, things don't always go according to plan. And sometimes the relationship between these two separate databases can become tenuous, or it can break entirely. This is what we call the data inconsistency problem, data parity problem between your online and your offline feature store. And this is a problem that if you use two separate databases, simply can't be avoided. Here at Splice Machine, we were lucky enough to talk to one of the original designers of the concept at a feature store at one of the tech leaders. We asked about this very problem. We asked, how much of a challenge is it to keep your online database and your offline database consistent? And he said it is the challenge. It is a fundamental problem of the feature store, and it's why traditionally doing real-time machine learning is so difficult. You have to maintain parity between these two separate data sources. Splice Machine's feature store takes an entirely different approach. We use a single hybrid database. Because data is stored just once in one location, you never have to worry about that online and offline consistency problem. How does Splice Machine's hybrid database work? We've all sort of been taught for as long as we've been involved in data analytics. It's an entirely separate process to do a quick primary key lookup versus a big batch aggregation. And that's certainly true. Splice Machine's innovation is a cost-based optimizer and separate execution path, depending on the type of query. So very briefly, if you have a primary key lookup, we'll execute that through HBase. If you have a big batch aggregation, we'll execute that through Spark. All of this is to say, we're able to do both kinds of analytics with just one database. What that means is that instead of having two separate databases, an online database and an offline database, we can simply have two separate tables inside of the hybrid database. We have our quote unquote online table, real-time feature serving table. These are the most up-to-date values of any given feature. And we have our offline table. This is a historical representation of how features looked in the past. These two tables are linked with ACID compliant triggers, meaning it is impossible for there ever to be inconsistency between your online and your offline tables. This guarantee, this assurance that your feature store is always consistent, is a guarantee that only a single database design can guarantee. So that's enough about the feature store. Now I'm going to transition to model deployment. Model deployment is very important for real-time machine learning. The traditional way that this is done is with a REST endpoint, where data is sent to an endpoint and a prediction is returned. This is a great way to return machine learning predictions, but it is challenging to govern machine learning when you do it in this method. You have to institute some sort of log search to get that data, the predictions and the features that cause those predictions sort of back into your machine learning pipeline. Splice Machine takes a different approach. We tightly integrate machine learning deployment with the very same database that is powering the feature store. Whenever you deploy a machine learning model, a table is automatically created inside of the database. And whenever a machine learning model prediction is asked for, the features that were sent to that prediction, as well as the prediction itself, are automatically stored and memorialized inside of a database table. This makes it very easy to use these predictions in future machine learning models, and then go back in time and see the impact of your models, how features have drifted, or perhaps check why a particular prediction was made at some point in the past. And so that's enough talk, enough sort of overview of Splice Machine, what we're going to talk about today. Now it's time to get into the hands-on workshop, why I'm sure all of you joined the call today. So what's going to be the structure of the workshop here? What are we going to do today? First is I'm going to walk you all through signing up for Splice Machine's free trial. I'm going to show you guys how to upload data to the database, open Jupyter Notebooks and query the database. Then I'm going to show you guys how to create a feature store from scratch. From the beginning, all of the steps, raw database to feature store. Then we're going to use that feature store to search for machine learning features. We're going to train a machine learning model using those features. We're going to deploy that machine learning model as a production-ready model. And finally, we're going to use that feature store as well as deployment for model governance. We're going to go back in time and track how model drift and feature drift has occurred. So before we get started, I want to highlight the brand new user interface that Splice Machine is launching next month. So that's not what I'm going to show you guys in the demonstration today. I'm going to show you our workshop user interface. But I want you guys all to be aware we have a brand new modern user interface launching in April. And by the next workshop, we'll be able to show that to you guys, and you guys can test it out for yourself. So now it's time to get started with the workshop. I'm going to go ahead and post this link here in the chat. If you guys navigate to this link, it'll send you to a sign up page, and you will be able to sign up for Splice Machine's free trial. And after you've signed in, you're going to have to, if you've signed in with your email, we're going to send an email to your email address. You're going to have to confirm that. If you sign in with something, with one of the OAuth tokens, using LinkedIn or Google or something, it'll send you directly to the homepage. You'll see a big screen. It says start 14-day trial. After you click on that, you should see a page that looks like this. So I'm going to wait here for just a moment, give you all a chance to get to this page, and then we'll get started with the hands-on demonstration. Moreover, the chat and the Q&A are open. So if at any point you have questions, I certainly invite you to post those in the chat. Where is the link? That is a great question. I posted it to panelists and attendees. I just posted in the chat. Let me know if you can see it. Great. So I'll give you all just a few minutes. Like I said, once you sign up for Splice Machine, and it can confirm your email address if necessary, you'll see two big boxes. One of them says 14-day trial. Just click on that. And you should wind up on a page that looks something like this. Okay, so just going to wait just a couple more minutes to give people a chance to get all signed up. Okay, so it looks like we have a number of signups. I'm hoping that people have made it to this page, and now we're gonna get started with the workshop. So the first thing that we're gonna do is take a look at the database, what's sort of underlying Splice Machine. As I mentioned, Splice Machine is built on this hybrid database. I'm just gonna show you guys how that works. So what we're going to do right now is something that's a little bit funky. This is just for the free trial. This is just necessary for this, big group distributed environment. This is not exactly how it would work in the commercial version of Splice Machine. What we're going to do is we're going to click on this link right here that says retrieve free trial. You're ever going to see that everybody's username is Splice, and then they have their own password. We're going to go ahead and we're just going to copy this Splice Machine password, and we're going to click right here on SQL Client. And when you do that, a brand new page is going to launch. You're going to type in Splice as your username and that password that we copied as the password. And we are going to wind up here in our SQL editor called Hue. Those of you who are not familiar with Hue, Hue is a very common way to interact with databases, and it has a lot of really great functionality just to see some of the data that we have here today. So as you'll see here on the left-hand side, we can see all of the different schemas that are inside of our database. We can see one called Feature Store. We can see one called Retail, Retail FS, Retail RFM. We have all these different tables. So in the demonstration that we're going to do today, we're going to focus on a retail example. We've got some retail data, and we're going to use that to build a feature store. So what we can take a look at is Retail RFM, for example. We can see customer category activity, and it'll show us all of the columns that are in this table. So we can do a quick little select statement here. We can select star from this table, and we can see it has this great autocomplete feature. We can look at customer category activities, throw a limit statement in there, and see all of the data that is inside of Splice Machine already. So here we have some data that's already loaded. If you wanted to add data to the database, there's a couple of ways that you can do that. The first way that you can do it is to upload data directly from S3, of course. We also, if it's a small piece of data, have this ability to just sort of click and add data into the database. So there's a number of different options, but underlying Splice Machine is a SQL database. It does both analytic and transactional queries. It's fully ACID compliant, and it's something that I think most data analysts and data scientists will be reasonably familiar with. And so now that we just sort of have the underlying components, the database sort of upon which everything is built, we can move on to the feature store itself. So you guys can go ahead and click on Notebooks here. This is going to open up a Jupyter Notebook page. So I'll give you guys a minute just to sort of get to here, and you'll have these 3 links right here. So in terms of how we get to the database, you get to the database once again by clicking on the SQL client. Okay, so you click on SQL client, you can see the SQL editor. Was there a SQL command you want us to type into Hue? If so, you could post it. Nothing particular that needs to be done for the purposes of the demo. I just wanted to show you that built into the system is a database. There's nothing particular that needs to be done. I just wanted to show you, we've got some tables, we've got some data sort of pre-added. You can query it sort of like any other database. That's sort of the purpose of showing you this part right here. Great. So just a quick flash of Hue now that that's over. Once again, just go ahead and click on this Notebooks link right here, and you'll get to a Jupyter page that looks like this. For those on the call who are not familiar, Jupyter Notebooks are a very common way that data scientists and data analysts write code. It's sort of a notebook-based way of interacting with very common programming languages, and sort of that's the way that we'll do the demonstration today. Of course, if you're more comfortable writing code in a in a code editor, in PyCharm or something like that, certainly you can connect to the Splice Machine database and do it that way. So hopefully all of you have been able to get to this point here. And what we're going to do is click on this link that's added right here called Workshop, and you'll see a number of different notebooks have been pre-added for you here. You guys can, if you guys would mind, go ahead and just clicking on this first one here, create a feature store, and it'll take you to a link that looks just like this create a feature store notebook. So in this notebook here, we are going to do sort of exactly what it says. We are going to create a feature store from scratch. So what we have in the database is, we've got some tables added, but we don't have, what we're going to do right now is make what we call a feature set. So the first step of, and I should mention that before we run anything in Splice Machine, we go ahead and we start our Spark session. Splice Machine is built on Spark. Spark is the sort of engine that powers the entire Splice Machine system. Splice Machine from the ground up is built for big data analytics, and so we leverage Spark in that way. And so at the beginning of every notebook, we'll have to start a Spark session. At the end of every notebook, we'll have to end the Spark session. So that's just, that's all that's sort of going on here, starting the Spark session, getting the feature store set up. We'll just sort of have this block of code in every notebook. So the first step to create a feature store is to create a schema. I had to click trusted for the notebook to run. Okay, that's a good point. Thanks for letting us know about that. We'll look into sort of why that was the case. So if you go ahead and click select schema name from systables, this schemas, this will tell you all of the schemas that are inside of the feature store. We're going to make a feature set inside of the schema retail FS. You'll notice inside of the schemas that retail FS has already been made for you. And so you don't have to do anything here. But the first step would be to create a schema to put your feature store in. So now that we have a schema where we're going to put our feature store in, we need to make what we call a feature set. A feature set is empty tables inside of the database that we will populate with data. So how do we do this? It's pretty simple. We have this function called create feature set. We specify the schema name in the database, and we specify the table name, and then we give this function sort of all the information we need to build our feature store. We have the table name. We have the primary keys that this table is going to have, and then we can give it a description so that future users can sort of understand what this feature set is all about. We then add features to the feature set. You can think of these as columns inside of a database table, right? Each one of these columns is a feature set, is a feature, I should say. So what pieces of information are we adding here? We're adding the name and the table. We're adding a description about what this feature is all about. And then we're going to give it some additional pieces of metadata. We're going to say, what type of data is this? Are we expecting an integer or a double or a date? We're going to say, what type of data is this? Is it categorical? Is it continuous? And we're going to give it a tag. We're going to say, tags are just sort of arbitrary pieces of metadata that can be added to the feature store such that features can be searched in the future. So we might have an entity, a calculation, a metric type, sort of any arbitrary information can be added to these tags. And as you can see here, now that my Spark session is all started up, we can see it registering these features and these feature sets inside of the feature store. And so registering feature sets, features, deploy, what is happening here? Like what is the point of these functions? Why aren't we just making a table inside of the database? Like what's different here? We're not making a single table inside of the database. With this function, create feature set, adding feature to that feature set, and then deploying that feature set, what we are really doing is we're creating two tables inside of the database. And these two tables are linked with an ACID compliant trigger. So how does this work? We have this left-hand side real-time feature serving table. This table will keep only the most recent value of a particular primary key. Then we have this right-hand side historical table. This is the historical representation of how data looked in the past. So as new data is added to the real-time feature serving table, only the most up-to-date values will be kept in this table, whereas a time series representation, historical view of all the features of the past will be kept in this right-hand table. And they are linked with this ACID compliant trigger, which sort of moves the data from one to the next as appropriate. That is what this function is creating for you. We have simply two empty tables inside of the database that are linked in this way. And once again, continue to just sort of ask questions in the chat about this process, but two empty tables inside of the database. The next step, of course, is to add data to these tables, right? There are essentially three ways that data can be added to the table. The first, simplest, fastest, and what I'm showing in the demonstration today is you can write arbitrary SQL to fill in these tables. You can take sort of all the most up-to-date values, put them in the real-time table, take all the historical values, put them in the historical representation table, and that's how the feature store is filled out. Here I have a question, will it be too heavy for the server if we keep a new version after each update? That's an excellent question. So a few things to mention. Splice Machine is built on a scale out architecture. At no point are we reliant upon a single server. Splice Machine is distributed. And so we can always add additional compute nodes if necessary. The largest instance of Splice Machine that I'm familiar with is about 13 petabytes of data running on a single Splice Machine cluster that is able to maintain predictions in milliseconds. Now, is it the case you might not always want to keep all of the historical values, right? Maybe you only want to keep the historical values of the last year. Maybe you only want to keep the historical values of the last 6 months. It is very easy to purge this historical table in two ways. One way is it can just be deleted. And the second way is it can be pushed to S3 or Azure Blob Store or something like that for sort of long-term storage, just for compliance reasons, building training sets built on years and years of data, that kind of thing. So day-to-day use case of the feature store, we are not concerned about this table sort of ballooning and becoming too large due to our scale-out architecture. So thanks for that question. That is an excellent question. So now we have these two tables inside of the database, right? And as I mentioned, we want to populate them with data. What we're showing here in the demonstration is just filling them out with arbitrary SQL. This is a wonderful feature of Splice Machine's feature store in particular. Because we're built upon a single database, we offer the users unprecedented flexibility. You're not reliant upon our APIs. You don't have to sort of, if there's a type of feature generation that you want to do, and we don't kind of have an API that supports that, no problem. You can write any arbitrary code to set up your features. However, this is not always a practical way to do it. Certainly, asking data scientists to write their own code can be error prone. And there are you might want APIs to sort of assist in that process. We offer the same APIs that everybody else does. You can sort of define arbitrary SQL that'll sort of do moving aggregations for you. I'm not showing that in this demonstration here just for time. I really wanted to highlight the differentiation here, right? Why is Splice Machine different than other feature stores? We allow you to populate the feature store this way if you so choose. Moreover, and very commonly, you'll populate these tables with real-time pipelines. The whole point of a feature store is that it's real-time. Splice Machine will just act as your consumer of, say, a Kafka stream or a Kinesis pipeline, something along those lines. Data streams on in. Old data is moved from the feature serving table to the history table. You have a fully functioning feature store, always kept consistent due to our single database ACID compliant structure. So now we sort of populated these two tables in the database, and we can sort of show you what they look like. So this first one here, we have the customer lifetime feature set table. As you can see here, we specified customer lifetime. That's the table that we created. And you'll see here, we're taking for a particular customer ID, we have the most up-to-date value for this customer. So this is the last time it was updated. These are those features. These are the features we have for this particular customer. Then we have this historical table. This history table was made automatically for you by that API I showed at the top. And here I'm just doing a limit statement so you can see the most recent sort of two values. But as you can see, we have this concept of an as of until timestamp, right? What were the periods of time in which these particular feature values were seen? As you can see here, some feature values changed. And we can see what was the range of time in which sort of the feature universe looked like this. If we wanted to update the feature store, it's simply an update statement in SQL. We're just going to update the most up-to-date feature set. Just one table we have to update. We don't have to do an update to both tables. We're going to change one of the values of the features. Hit go, and then we can run this table here. And we'll see that this most recent value, this change of customer active days from 10 to 11, has been reflected inside of the feature store. And then that old value, the historical value, has automatically been moved to this historical table. So now we have here, as you can see, it went from last year up until just now when I made this change. And we have this, this new value, this new feature value automatically represented inside of the feature store. So this is the structure of the feature store. This is how it's built. And the differentiation here, why Splice Machine is so powerful, is that it's flexible. You can add data however you need to the feature store. It's versioned for you automatically in a scale out way. And the history of that data, as well as the most up-to-date versions of that data, are always kept consistent. So now important that we stop the Spark session, not sort of use any unnecessary resources on this particular notebook. What we have here at the bottom is this form. What I would love for you guys to do, for those of you following along at home, is if you have any feedback on setting up the feature store, we would love for you to put that here. And then in the future, we'll have the ability to improve the workshop. So I'm just gonna stop this here, give you guys a moment, and I'm gonna move on to this second notebook. You guys go from 1 to 2, open up feature discovery, which is where I'm at right here. And I'll wait just a moment for you guys to get to this space here. Excellent. So I'm going to go ahead and move on to the second notebook here. So what I did in the first notebook, what we did together is we built a feature store. We have a fully functioning feature store built. Now we need to go ahead and use it, right? What do we do with it? Feature stores, as I mentioned in the quick presentation at the beginning, do 4 things. And the first is feature discovery. We have a repository of all of the features that have been built, and we can use those for, we can see the features that are available to us. Now, in the last notebook, we built a feature set, but what you'll notice is that a second feature set has already been built for you. Your environment just sort of, the environment that we built for this workshop just comes pre-populated with an additional feature set. And so how can we see all of the feature sets that are available to us? We can call this function that's a part of the feature store called describe feature sets. And what it'll show to us is all of the feature sets that have been built, the one we built in the last notebook and the one that is already pre-populated in this environment. So you'll see here, we have 2 different feature sets. This first one is RFM by category. This we did not build, this was here already. If we want to know what this data is all about, we have a nice little description. We can see what the primary keys are, and we can see all of the different features that are in this feature set. And then we can do the same for the feature set that we built in the last notebook, this customer lifetime feature set, and those 8 features that we added to that feature set. It's going to see the name, description, integer, all these different things. In this particular case, we have only 2 feature sets, but you can imagine there being 200, right? This is certainly not, this is a nice little quick representation. You can see what's out there, but this is by no means, a scalable way to search for features, which is why we offer this, this feature search capability. We have a search bar built into the feature store that makes the cataloging of features scalable. So here we can see all of the features that we have in the feature store, 176 of them. We have the name, description, tags, like the last time this feature set was updated, all these pieces of information that are really valuable. As I mentioned at the outset, we have a retail data set. We have data from a particular retailer. I might say I want to know all of the data from the deli, for example. I can go ahead and click on that feature, and it'll automatically build for us the feature distribution of this feature set. So this makes the cataloging of features scalable, right? All the different teams can sort of add their different features to this feature store, and all the different team members have the ability to see all the features that are available to them. One thing I want to mention is that underlying this whole search capability is SQL, right? We essentially wrote, we wrapped a Python package around a SQL statement. to generate this. And so if your organization needs some kind of custom search capability, there are particular things that you guys are always looking for. You need to add in your own custom visualizations. We're certainly improving on our search capability all the time, but you are by no means restricted to our search capabilities. Your data analysts or data scientists can easily write SQL, extract all of the raw data out of the feature store, and make whatever custom search capabilities are necessary for your organization, which is possible because of our sort of one database design, right? You don't have to worry about sort of getting data from the two different places. It's all unified. And so that's sort of the rundown on the search capability. We can go ahead and stop the Spark session. Once again, if you want to take a quick survey, we would love your feedback on this this part of the feature store. At this point, I'll move on to the third workbook, which is model training. And once again, if there are any questions, I would certainly love to hear those. So I'll wait just another minute, just so everybody can get on the same page here. Okay. So we've talked about the first use of the feature store, which is feature discovery. And now we can move on to the second use case of the feature store, which is building training sets. So in real-time machine learning problems, why is building training sets a challenge, right? Data scientists build training sets all the time, on sort of big batch data. They add a column, for their label. They sort of remove it when they're building their training set. What's the challenge here? There's a particular challenge with real-time machine learning training sets that we call the point-in-time correctness problem. In other words, you want to make sure that you are training on the data that is available at prediction time, not at the time that you get your machine learning label. And so this is kind of a tricky concept. I don't really want to go into too much detail here, but just understand that when you're making predictions at multiple periods of time, you're going to have the labels, the predictions are going to change. And the time of prediction is not necessarily going to be the time that the label gets to you. And so it's very easy, say, if you're making a prediction at this period of time, to accidentally add in, say, a feature that was created after that prediction was supposed to take place. And this particular prediction happened at this point, and you add in, feature value 7 here, the number of sessions in the number of products that have been viewed. That's data leakage, right? That's data that the model should not have had access to. Moreover, it's easier to sort of undershoot. Maybe you get all of the feature values as of this particular point in time, and then you're missing the most up-to-date data, and your model is not going to be as accurate as possible. So this is a challenging problem, and it's certainly one that your data scientists can solve, right? We don't mean to say that this is impossible without a feature store, just that it's very difficult. And for every additional model that you have to create, you have to make these very complicated point-in-time joins over and over and over again. So maybe you can do it once or twice, but what about for your 5th or for your 50th model? So to build a point-in-time consistent training set that looks like this, where the timestamps are different for different customer IDs, and we have a consistent label, and then the training, the most up-to-date values as of a given point in time, this is a challenging thing to do. And this is what a feature store can do automatically. So how does that work? Go ahead and start my Spark session here. As I mentioned before, we have our 2 tables. Now we can use this right-hand side, this historical representation of data to build our training sets. So how does this work? First, we start with any arbitrary SQL to get our training label. This arbitrary SQL does not have to be inside of the feature store. You don't have to have a feature set that contains your label in it. Just any arbitrary SQL. It doesn't have to be inside of the Splice machine database. If you want to query your data warehouse or your database or your data lake or whatever, that's great. Splice machine allows for external table functionality as well as what we call a virtual table interface. In other words, if you have data sitting in, let's say, a hive table, we can query that hive table and get the data into Splice machine, temporarily without having to sort of have it duplicated in both places. So you get your label from wherever it exists. Then all you have to do is specify the primary keys of your training label, as well as the join keys. What do you actually want to join on? And then the feature store will go ahead and build for you that training set. It'll find every single feature inside of the feature store that matches those particular join keys and primary keys and pull them in a point in time consistent manner. So what we've done here is we've just created this concept of a view. I'll explain what that means in a second, but we can go ahead and just get this training set from view. And as you'll see in just a moment, we're returned a Spark data frame that is our training set. So this will take just one more moment here. It is Spark after all, so it's not optimized for those real quick small lookups. And so as you can see here, we have our training set. We have the primary keys that we're interested in. We have the timestamps. We have all of the different features, and then we have this training label automatically built for us and combined. In this particular case, we're only taking data from two different training sets, or two different feature sets, I should say. But you can imagine this being much more complicated. You can imagine there being 100 different feature sets that are all being combined in some way for a particular training set. And there's sort of no additional complexity from the perspective of the data scientist when the complexity of your data increases. It's still this one function. So I want to draw a differentiation here of how we are building training sets versus another way you might imagine a feature store building training sets. If you'll notice here, what we're building is what we're called a training view. This is literally a view in SQL, right? This is a structure of a query, but every time this query is rerun, you will get the most up-to-date data. You'll get the new data. And so that's what we do here. We're saying we're going to get training set from this view. We'll get all the most up-to-date values. As data is streaming in, you can imagine the data inside of this training set is going to change. And if we were going to rerun this, you'd get all of the most up-to-date data again. So when you run a data in one moment, when you run a feature, get training set one time, and then if you run it again a day later, you're probably going to get two different training sets. Of course, you can specify, a from until timestamp here if you want to get the exact same training set every time. But by design, we've made it so that every time you rerun this, you get the most up-to-date data. What this works under the way this works under the covers is literally just a SQL statement. We'll see here the SQL statement that is used to create this training set. It'll be printed out in just a moment. And every time you run, get training set from view, all it's doing under the covers is rerunning this huge SQL statement again. So why is this a benefit? This is a benefit for two reasons. First of all, it empowers very easy retraining of models. Imagine your pipeline that is retraining your model, let's say every month. In order to get the training set for the retraining, you don't have to change any of your code. You just get the most up-to-date data right out of the feature store for your retraining pipeline. Second, in this conception, you don't have to unnecessarily persist data. One way you might do this is every time you get a training set, you take that data frame that is your training set and you throw it in an S3 bucket and it sits there forever, right? It just exists, eating up your S3 costs, and it's stored. Splice Machine takes a different approach. What we do is whenever you create a training set, we log a timestamp and we just say, this is the timestamp at which it was created. We just have to log that one thing. And so if you want to recreate a training set exactly as it looked some point in the past, we can just rerun this SQL query with a timestamp, right? Just say as of the particular time in the past. And what we're able to do is have end-to-end governance, know exactly what training set was used to build any particular machine learning model without actually having to persist that training set. Other platforms require you to persist that training set. Certainly that is a good solution for smaller data, but in Splice Machine, where we're most familiar with terabytes and petabytes of data, certainly not a scalable solution, and this is the way that we've solved it. So I do want to highlight very quickly the complexity of this SQL query. This is what was necessary to build this training set, right? This is a very complicated SQL query for a novice data scientist to write. We have subqueries, we have inner joins, we have outer joins. There's a real opportunity for error. This is an error-prone process, building training sets. And once your feature store is created, as I demonstrated a few notebooks ago, building your training sets is pretty much automatic. So the next step here, this is the part of the code that takes the longest. So just to give you a heads up on this particular line, will take some time. What is the value of being able to automatically build training sets? Your data scientist might say, I am perfectly comfortable finding all the features that I want, pulling them in, doing those point in time joins. Like, I don't need you to do it for me. What's the benefit? What we are doing here is finding every single possible feature that can be added given the constraints that you specified. Given your primary keys, given your join keys, we are bringing in everything. In this particular case, we have 120 features that are added. You might imagine it being 1,000 or 10,000, right? We give you everything. And so what that allows data scientists to do very easily in just one line of code, get everything, then you can do your feature selection. In this case, we have an automatic feature selection algorithm that's built on Spark. This is one that we wrote here at Splice Machine. By no means are you constrained to using this particular feature elimination algorithm. You can use any feature elimination method that you would like. But when data scientists have access to all of the features and they have it so quickly and so easily, they have the ability to do feature selection like this, right? They can feed every feature in there and figure out exactly what's going to be most performant, really without any additional work from the perspective of the data scientist. So here, as you can see, we're returning a new training set, right? We're returning this model training data frame. It's the same function we read before. It's this get training set from view using this training view that we created before. And then we're just specifying to take only the top 10 most performant features. You could, of course, add this in manually as a list, but in this case, the list was generated by this function here. And so you can see it sort of chugging along here, getting the most up-to-date features, and should be done in just a second now. Great. And so now that we have our most performant features, it's probably unlikely that your data scientist wants to put all of the columns in a particular model. We have those 10 features that we think are most performant. We can go ahead and train our machine learning model. So in terms of the training of the machine learning model, I don't think there's anything particularly special going on here. I think that the training of machine learning models is more or less a solved problem. Data scientists have really an incredible amount of tools at their disposal, in open source packages from H2O to Spark to proprietary methods that might exist inside of your organization. Data scientists at this point, I don't think need any help training their machine learning models. Certainly building their training sets, but writing their H2O code, is sort of what they're there for. And so Splice Machine in our system, we have Jupyter notebooks embedded. In this case, we're just making a real simple Spark ML linear regression model. This can be sort of arbitrarily complex. What Splice Machine has added inside of the system is MLflow, and this is not regular MLflow. This is a custom fork. This is a fork of MLflow that we've made here at Splice Machine that offers some additional functionality and makes it really easy to use the feature store. So what is MLflow? I can go ahead and run this code here. Let's give us the MLflow UI. MLflow is this method of tracking the machine learning lifecycle. All it does is sort of log in one place, all of the machine learning models that you've run, different sort of parameters and tags and sort of anything you need to know about your model, sort of all logged in one place. Splice Machine, we're really proud of our ML flow integration. But once again, if you want to train your machine learning models in another platform, that's great. What the feature store will do for you is automatically build the training set necessary to do so. So what we're going to do now is just store those most performant features so we can use them in the next notebook, and that's it. We've built our training set from 2 different sources that are updated at different points in time, and we've trained our machine learning model using it. If there are any questions, I'd love to answer, and we can move on to the next notebook, which is model deployment. So what I demonstrated in the last notebook was using a feature store for model training. And that's certainly an incredible use case of the feature store. The ability to automatically build training sets for your data scientists is really quite valuable. But the real use of the feature store, why so many companies, Airbnb and Facebook and Uber and Google, why all of them needed a feature store, was the ability to serve features to deployed machine learning models. This is the hard part, right? When you have a REST endpoint, it's easy enough to add data to that, throw data at that endpoint and get a prediction back. But how are those features generated? If you have some sort of feature generation pipeline, you've got a moving window aggregation, for example. How can you send the result of that moving window aggregation to the deployed model? It's very tricky to do. And so the feature store, once again, does that for your data scientists and your data engineers, ML engineers, automatically. So quickly, in terms of how we're going to deploy a machine learning model in this particular workshop, we're not going to do it in the traditional REST endpoint method. Certainly, by all means, you can set up a REST endpoint, get data out of the feature store, send it to the REST endpoint. That's great. But we're going to do a different method today, and that is what we call database deployment. How does database deployment work? As I mentioned briefly during the presentation, we build a table inside of the database. It has columns, one for each feature, and then additional columns for the prediction. It could be one column, it's a binary. It could be multiple columns, just whatever the prediction is, as many columns as necessary for that prediction is what we have in the model. And the way this works is every time a row of data is inserted into the table, the features are inserted into the table, the prediction is automatically generated and stored in that same database table, along with some metadata. Who asked for the prediction, when, what model was used to execute that prediction. Why have we chosen to deploy models in this way? First of all, it's fast, right? Splice Machine is a transactional, ACID compliant database. We use HBase as our key value store. We're able to execute predictions in milliseconds. This is different than database deployment in a data warehouse. Redshift ML was launched late last year, and it's a great platform, excellent for doing batch machine learning. But of course, Redshift is not built for a real-time use case, right? You wouldn't insert a row and get a prediction back in milliseconds. Splice Machine is a transactional engine for that. Second, it's easy to deploy and govern. As I'll show you in a moment, setting up this deployment mechanism is just one line of code. Moreover, data governance couldn't be any easier. All of the data necessary is stored inside of this table. Everything you need for governance purposes, for regulatory compliance, it's all stored here automatically. And finally, it integrates really nicely with the feature store, which is what I'll show you in just a moment. So how does this database deployment work? What we're going to do is we're going to get out of MLflow the model that we've just deployed. So I have a few more models than you all do, as I've run this code a couple of times. But you can see sort of the model we ran most recently, and you'll see here we have this concept of a run ID. I'm just going to go ahead and copy that. Just copy that run ID right here, and then I'm just gonna paste it right here where it says run ID, and we'll get to this line of code in just a moment. So obviously, in this case, we trained a machine learning model inside of the Splice Machine platform. What if you're not using the Splice Machine platform? What if you're using Databricks? What if you're using Dataiku? What if you're using just a Jupyter notebook on your personal machine? That's no problem. You know, you can, we have a function that'll take your deployed model from Databricks, send it right to the Splice Machine deployed, the database deployment can come from anywhere. By no means do you have to use sort of our Jupyter notebooks. The feature store can be used anywhere. I have a great question in the chat. The question is, do customers use Splice Machine interact with Spark graph frames? So because Splice Machine is built on Spark, certainly we have support for you know, Spark's graph capabilities. One thing we haven't done yet is use the feature store in a, you know, in a graph way. We haven't sort of implemented sort of a full sort of graphical sort of use case of the feature store. It's certainly something that we're looking at in the future. And we would love to sort of talk more about how that might work if you know, particular graph use cases are necessary at your organization. So thanks for that great question. So now we've got a trained model, it can come from anywhere. We're gonna go ahead and deploy it inside of the database. So first thing we're gonna do is we're just gonna run this line of code. All it's gonna do is just get those most performant features that we used in the past. We're just gonna drop this deployment table if it exists already, which on your platform they won't. And then we're gonna run this single function, mlflow.deployDB. You'll notice in regular MLflow, there is no function called deployDB. This is a function that we wrote. This is part of the Splice Machine MLflow fork. And so how does this work? We specify a table inside of the database, deployed models, retail regression is what we're gonna name this model. We specify a run ID. This is that MLflow model. Specify some primary keys. Then we specify the training set that was used to create this model. The reason for this is we need to tell the model, we need to tell MLflow, you know, what columns to make, right? What are the columns that, what should this empty table inside of the database that we're making, what should it look like? And so what is actually happening? What have we done here? Like what is all this? I've printed out the logs here so you can kind of see what's happening. Like what is happening? We've done two things. We've created an empty table inside of the database, and we've created a trigger. And what that trigger does is whenever a new row is added, it calls a user-defined function. The user-defined function is the machine learning model that you created. And whenever a new row is added, that trigger fires, calling that user-defined function, your machine learning model is generated and a prediction is stored in that same table. So that's our approach to machine learning deployment here at Splice Machine. We think it is particularly useful in a lot of real-time applications. By all means, you want to deploy models as a REST endpoint, great, we support that as well. So now we want to get data out of the feature store and send it to our deployed model, however it's deployed. How do we do that? We get it out of this left-hand side real-time feature serving table. These are all of the most up-to-date values of a particular feature. This table, as I'm sure you can imagine, is gonna be much smaller than this table, right? This table is going to have one value for any particular key, for any particular, you know, primary key. And so primary key lookups on this table are very, very quick. Millisecond speed due to our HBase key value store. So we're able to get data out of the feature store very quickly and send it to a deployed model. And so what does that look like? We can do it in a couple of ways. First thing we could do is return our feature vector, which is the term we have for those most up-to-date features, as a Spark data frame. This is certainly not what you would do for real-time use cases, right? This is useful for big batch machine learning jobs, right? You might want to get hundreds or thousands or millions of features out of the feature store, and we can return that as a Spark data frame. But that's not what you would do for a primary, you know, for a deployed application. What you would do for a deployed application is you would generate a parameterized SQL statement, right? We have this SQL statement that is generated. This is all of the data. This is the SQL necessary to get the data out of the feature store based upon the features that we specified. So we can go ahead and copy this, paste it right below, and see how fast it is to get those most up-to-date features out of the feature store. As you can see here, it took 1.1 seconds. This, of course, is not sort of the real time, right? It's in fact much, much, much faster than this. This is the wall time of the Jupyter Notebook. I'll show you at the end of the presentation a more accurate representation of how fast this looks. Of course, you never have a deployed model, running in a Jupyter Notebook, but this happens in milliseconds. And so you would write a parameterized SQL statement, give that to your engineers, pull data out of the feature store, send it to wherever it needs to go. Now, at this point, I want to pause, and I want to re-emphasize this point that I made during the workshop that not all feature stores are created the same. You'll see here that this sort of architecture, right? This API, this get feature vector, is very similar to what you'll see in all feature stores, right? Sort of the space has sort of converged around this idea of feature sets and feature stores, maybe calling them slightly different things, but we're all kind of on the same page, the same idea. But you'll notice that the underlying architecture is not the same among all these different providers. What I have here is a screenshot from another feature store. I blacked out what feature store it is because it doesn't matter. Lots of feature stores have lots of different incredible functionality, some that the Splice machine doesn't. But this particular problem is something that applies to really any feature store that's built on two databases rather than one. And this is the idea I mentioned at the beginning of inconsistency between your online and your offline feature store. What happened in this particular demonstration is of another feature store is they did exactly what they said. We're going to get features out of the feature store, set a particular primary key, get those features out of the feature store. We get an error. It says we don't know what you're talking about. There are no features in the feature store. So in this particular case, features were added to the offline feature store, but not added to the online feature store. And so when it came time to actually deploy the model, the features weren't there. And this is a problem this is the reason that real-time machine learning is so hard, right? Keeping consistency between the data that's used to train your models and the data that your deployed models actually seen is such a challenge, and it's solved in the Splice machine system by the single database architecture. So here's how you get features out of the feature store. How would you send it to a deployed model? It's as simple as an insert select SQL statement, right? Insert into this deployed model, select data out of the feature store. What is this SQL statement? It's just a parameterized version of the one that this feature store generated for us. So nobody has to do sort of any thinking here, right? It's not like a hard problem to figure out how we get the most up-to-date features out of the feature store. The feature store just writes that SQL for you. It says, here you go. Here's the optimized primary key, best way to get the data out. Have fun. So what we've done is inserted 2 rows of data into the feature store, and we can go ahead and see what that looks like. We can see all of the features that we've added, which are here. We can see this prediction, which is automatically generated and stored in that same database table. And then we can also see some metadata. We can see who asked for the prediction, when that prediction was asked for, and the run ID. This is the model that was used to make that prediction. We can then go back into MLflow and say, what is this model? How is it trained? Who trained it? All that kind of stuff for governance purposes. And so because of Splice Machine's H-based evaluation, because of our quick key value store, we're able to get data out of the feature store, insert it back into the feature store in milliseconds. And as I mentioned at the end, I'll sort of show you in SQL Shell sort of what that speed really looks like. And so if there are no more questions, I can keep on going, but certainly if you have any questions, feel free to ask. So what we've done here is a quick primary key lookup. This is great for real-time machine learning problems, but of course you might want to use the feature store for a batch machine learning use case. How would you do a scoring job on, say, 1,000 or 100,000, rows of data? Exactly the same idea. instead of adding a single row to the table, you just add a bunch of rows to the table. And the feature store, will write the SQL necessary. We have APIs that just sort of tell you how to get that data out of the feature store in the most efficient way. So we got a couple 100,000 rows here, that are running. The batch job is sort of going. It should take about a minute on this really small cluster. As I mentioned earlier, Splice Machine is scale out, and so the efficiency of this is more or less linear. So as you can see here, we have a bunch of different rows added, bunch of different primary keys, and you can see all the different features. And I guess I should say this is what was added to the table. And so that is model deployment. So the key takeaways are sort of twofold. One is the feature store in general, which is able to get data out of the feature store, exactly the same features that were used to train the model. It's able to do that in milliseconds. And the second is Splice Machine's custom database deployment mechanism that leverages our hybrid database. Certainly, you don't have to use that to use the feature store, but we think in a lot of use cases it's really a great mechanism. And so if there are no questions here about model serving, model deployment, I'm going to move on to model governance, which is, in my opinion, really the most interesting and different part of the feature store. So you all will notice in your notebook that these cells are pre-run for you. By all means, feel free to rerun them yourself. The reason they're pre-run is because they take a while. But I want to make the point here about model governance and feature governance and data lineage and why that's so easy with a feature store. So the first plot here, model drift, is something I think that many of you will have seen before, right? This is the distribution of model predictions over time. This we get out of that feature store table, and sort of in that model deployment table. A more traditional way to do this, of course, is you have your REST endpoint and you track your logs and put those logs in some kind of table format and build a similar plot to this. This is useful. We can track predictions over time. What the feature store can do is take this type of analysis to the next level. Because we know exactly the training set that was used to train any particular machine learning model, and once again, we're able to do that without persisting the training set. We're just logging timestamps. And because we know exactly the features that were sent to a deployed model, that's what's kept inside of that model deployment table, we are able to track the change in feature distribution over time. We're able to say in blue here, this is the distribution of features that the model has actually, this is the distribution of features that the model was trained on. And then in orange, we have, this is the distribution of features that the deployed model has actually seen. And so, in this particular feature, we can see they're more or less the same. And in this particular feature, we can see there's a difference. And this is something that the data scientists need to take a look at. So I've got a question in the chat here. It says, if you get an error in notebook 4 and then move on to notebook 5, would expect the second statement, see the distribution of predictions over time to cause an error. Caused by error deployed table regression does not exist. So I just want to make sure I have understood the question. You have an error in table 4. This table was not created properly, and then what happened is you ran this, and then this model this function just ran even though your model table doesn't exist. Is that what you're describing here? If so, it's a good observation. We're aware of that bug, and we fix it in the next release. If it's a different problem, let me know in the chat, and I would love to help you problem solve that. But the problem of if this table is empty and you run this table, it'll just put you out like an empty graph or a graph that doesn't make any sense. We know about that problem, and we fixed it in the next release. The second line is not actually running no graph. Right, once again, the error, the problem of the data not looking as the function expects. We're aware of that problem, and we're it's been fixed, and that'll be updated in the next week or so. But it's a good observation, and so thank you for pointing that out. So as I mentioned here, we've got this distribution of features, the difference between the data the model was trained on and the difference that the model was actually seen. This makes tracking feature drift really easy. Finally, we can really offer sort of unprecedented levels of data governance with the feature store. So here we have, imagine that a regulator or another member of your organization comes to you and asks, why did your model make this particular prediction at this particular time, right? What you can do is find the customer ID for what they're talking about, give it a time range, go back and find all of the individual features. In this customer ID I picked here, they're all zeros. Let's see if we can find a more interesting one. Yeah, I'll just go ahead and move this this time constraint so you guys can see what I'm talking about here. We can see all of the different features used for any particular, all of the feature values over time for any particular primary key, and we can see the difference in the predictions that are a result of those features. And so at any time, somebody can come to you and say, why did you make this prediction? And in just one select SQL query, you can say, here are the features that we had from the feature store at this time. Here's the prediction that was generated. Get that back instantly. Moreover, you can then go into MLflow and say, what was the particular model that was used to make that prediction, right? What are the features of that model? What type of model is it? Who trained it? What are the metrics of that model? You can even see the model itself. And then interestingly, you can see the machine, the Jupyter notebook that was used to train that model in the order that those cells were run. It's important for Jupyter notebooks. You run the cells in a different order, you get a different result. And so you really have an unprecedented level of data governance. And so this sort of concludes the feature store workshop. What I'm going to show you very, very quickly, as I promised, is just a quick demonstration of the speed. We keep talking about how fast Splice Machine is, but obviously a Jupyter notebook is not the way to do that. So what I'm going to do here is just open up a SQL shell terminal really, really quickly. What I'm doing here is I'm just copying the JDBC URL. I'm going to type in SQL shell.sh. It'll launch my SQL shell, connect, give it that JDBC URL. And then what I'm going to do is I'm going to copy that feature vector out of the feature store that it created for me. Put that in the SQL shell right here. And there you go. In this particular case, we had 145 milliseconds. Of course, if you had a stored procedure, it'd be much faster. This next time, it's only 13 milliseconds, right? So stored procedure makes it so you don't have to compile every time. All this is to say, getting features out of the feature store and serving them to deployed models is incredibly performant in Splice Machine due to our HBase under the covers. And so that is the conclusion of the Splice Machine workshop. In terms of what's next for Splice Machine, we have a brand new user interface launching this month, which I guess in April, I should say, which we're incredibly excited for. We have some new APIs. We have some additional APIs to manage backfill. You've got a bunch of data sitting in your data warehouse. How do you add that into the feature store in an efficient way? We've got some APIs that we're launching to manage that. We've got some more granular permissions. One of our clients is in the healthcare industry, and they have very specific, HIPAA constraints. And so some additional permissioning for the feature store is coming. And then, of course, the bug that was pointed out is being fixed in that next release. In terms of if you want to continue with Splice Machine, the cluster that you guys are all on is going to expire at the end of the session. However, if you want to continue with the free trial, feel free to navigate to our website or reach out to myself individually, and we'd be happy to get you on a free trial, for a longer period of time. Moreover, if you want to see the code that was used for this presentation, just send me a message. I'd be happy to share that with you. In terms of actually getting started, the best thing to do would be to reach out to myself. We can get you started on Splice Machine, if you want to sort of move past the free trial, or you could purchase it, on a per hour basis from the AWS marketplace. But really the best way is just to reach out to me, and I can get you going with that in just a few minutes. So thank you all so much. I'll stick around for the next 5 minutes or so if you all have any questions. But I hope you all enjoyed the workshop. The Splice machine interact with data fabrics. I'm afraid that I don't actually know what a data fabric is. So if you could, I'll certainly talk to Neo4j, great question. I am not entirely sure what that interaction mechanism would look like for a graph database. That is a really excellent question. I myself have not done that yet, but what I will do is I'm going to talk to some of the engineers in the organization. I'll get back to you with a clear answer about that. The diagram I've seen as featured is at a mid-level. Yeah, that's a really excellent question. I know that there are plans for our integration with that, but I'm going to, as I mentioned, send you some information on sort of exactly what our interactions with a graph database might look like. In terms of sharing you the code, I'll be happy to shoot you an email with that link so you can keep your hands on it. Moreover, if you want to do a free trial, you sort of have that workshop, have that workspace up and running for a longer period of time, I can set that up for you as well. Of course, this code isn't gonna, it probably won't run in your own sort of Jupyter notebook. This requires the Splice machine infrastructure around it. And so I'll be happy to, I'll follow up with you by email and set that up for you. And thanks so much for the feedback. Certainly, if you have any questions, please reach out. Please provide my contact information. Great. I'm going to go ahead and put my email in the chat here. All right. I just sent my email in the chat there, and feel free to send me, a message with any individual questions, and I'll get back to you with the code and how you might get started on a free trial. Wonderful. So I'm going to go ahead and end the workshop here. But once again, my name is Jack, J. Ploshnik at Splice Machine, or on LinkedIn, or really any way you like would be the best way to reach me. And look forward to seeing you all at the next workshop.